Hi, my name is Shahnawaz. In last lecture, we introduced the notion of paths. So let us recall the definition of a path. So if we have a topological space X, then a path in X is just a continuous map from the unit interval 0, 1 to the space X. So if this is the space X, then path f is just this curve over here. Now this is the initial point, say f of 0, and this is f of 1. This is the final point, and these points are called the end points. Then we discussed the operation on paths, and we also defined the inverse path. So if f is a path from 0, 1 to x, then the inverse path f bar is also a map, continuous map from 0 to x, such that f bar of x is same as 1 f of 1 minus x. Now if f travels from f0 to f1, then f bar travels from f of 1 to f0. Now we define the another operation that is called the product of paths. Product of paths. Now let us consider two paths in topological space X. Let f and g be continuous maps from this unit interval 0, 1 to x, be two given paths. Such that f of 1 is g of 0. Now if this is a space X, when we take f from 0, 1 to x, we go like this. This is f of 0 and this is f of 1. So f of 1, and it is given that where f has the end point, g has the initial point at that point. So this is same as g of 0. Now this is the path f. Now from this point g starts traveling to g of 1. So this is same as g of 0. So this is g of 1. So this path, this combined path, this is the product of paths f and g, and it is denoted by f dot g. Then the product of of paths f and g is another path. So if this is a path, then the product of the paths then the product path of paths f and g is another path fg. So this is a path. So it is a path. This is from 0, 1 to x, such that now it is given as, we define it as f dot g. So it is, so first we have to travel. So this fg travels in the time interval 0 to 1. So in the time interval 0 to 1, so this is our time interval 0 to 1, this is the interval 0 1. So in this interval we have to travel this path fg, such that in the first half interval we travel f, and in the next half interval we travel g. So if I have to travel path f in the half interval 0 to 1 by 2, f has to move twice as fast as the original f. So first we have to travel f in this half interval, so it has to travel at the twice speed, at the double speed in this interval 0 less or equal to x less or equal to half, and in the remaining interval, in the next half interval, now see y2x goes here as an argument of f, because on normalizing this interval, by normalizing this interval I mean we have to rescale it from 0 to 1. So while rescaling this interval from 0 to 1, this is same as if 0 is less or equal to x is less or equal to 1 by 2, this means 0 is less or equal to 2x is less or equal to 1. So that is why this 2x goes to here. Now in this remaining interval from half to 1, we have to travel g. So now we have to check what goes here, what goes in the argument of g. So in that case we have to normalize this interval. So on normalizing this interval, I mean on rescaling this interval from 0 to 1, what we do, we subtract half. So this is 0 is less or equal to x minus 1 by 2 is less or equal to 1 by 2. Now to make it from 0 to 1, we multiply 2. So this is 0 is less or equal to 2x minus 1 is less or equal to 1. So 2x minus 1 goes here. X minus 1. Note that f and g are continuous, so fg is continuous. Now to check it is continuity, it suffices to check continuity at half, because if since limit x goes to half minus, so this is since x goes to half minus f of g, that is limit x goes to half f of 2x, that is f of 1. Similarly, limit x goes to half plus f of g, f dot g, that is limit x goes to half g of 2x minus 1, that is g of 0. Now it is given that f of 1 and g of 0, they are equal, so this f of g is continuous at 1 by 2 as well. So f of g is a continuous function from the interval 0 1 to x, so hence it's a path. Now one can notice that this is not the composition. One should not get confused with the composition of functions, because in composition of two functions we first operate g and then f, while in the product of two paths we first travel f and then travel g. if it was composition, we would have another way around, because we are first traveling F then G, but this is not the case in the composition. That is why one should not get confused with the composition notation. This is the product notation here. So what actually happens here? So if this is the interval 0 and 1 and this is half, in this half interval I have to travel F. So F has to travel twice as much as fast, and in the next half interval I have to travel this G. So this is G here, this is F here, and this point is same as at this point F of 1 and G of 0 are equal. Now note that this product is not associative. Now what do we mean by that? So let us make a proposition here. Proposition: this product of paths is not associative. Proof: let us consider paths. Let F, G and H be the paths from 0, 1 to X. Now by definition of product of paths, by definition of product of paths, we have, now let us check what will happen to this. First we'll look at this product F dot G dot H. So in this product, or let us consider this product first. F dot G dot H. So this is one path and this is another path. So for this path F, we first travel this path and then this path. Now this overall product, this is a map from 0, 1 to the space X. So we have to split 0, 1 such that we first travel F, then G and then H. Now let us see what will happen. Now first we have these two paths F and GH. Now for F, it has to travel in the interval, suppose this is 0 here, this is 1 here. So we will reserve this half interval for F and this another half interval for GH. So 0 less or equal to X less or equal to half, we will reserve this for F. Now if it is reserved for F, now here on normalizing this interval, one can observe that 2x goes in the argument of f. Now to travel gh, we further split the remaining half interval. We first travel g and then h, so we have to split this interval into parts. This is 3/4 and this is so in this interval half to 3/4 we have to travel g. So 1/2 less than x less or equal to 3/4, we have to travel g. So on normalizing this interval, let us normalize this interval here. So 1/2 is less than x is less or equal to 3/4. So this is 0 less or equal to x minus 1/2. This is less or equal to 3/4 minus 1/2, that is 1/2. 1/4, sorry. This is 1/4. Now to make it from 0 to 1, we multiply by 4. So this is 0 is less or equal 4x minus 2, because am I doing, I think this is this is 4s minus 2 exactly. This is less or equal 1. So this is g of 4x minus 2, and finally in the interval 3/4 we have to travel h, and that is h of 2x minus 1. So this is the product f dot g dot h. Now let us check what is this product. Now f dot g dot h. So this is by definition. So we have the interval 0 1, and we break this into two sub intervals 0 half and half 1. So this is reserved for h and this is reserved for f dot g. Now this f dot g, we have to travel this path in half. Now on traveling this path, we first travel f and then g. So we have to split this interval into two halves. This is 1/4 here and this is 1/2 here. So f is reserved for for this h. What we do, we have to travel this h in this interval. So on normalizing this interval, 2x minus 1 goes here. Now in interval 0 to 1/4 we travel f. So this is 0 less or equal to x less or equal to 1/4. So we have to travel at a speed of 4 times bigger than the speed of original f. So this is 4x, and we have to travel g in this interval 1/4 is less or equal to x is less or equal to half. So on normalizing this interval we get this is 4s minus 1. So one can note that these two functions, they are not equal. So this is not associative. Observe that f dot g dot h is not equal to f dot g dot h. Now let us define the path homotopy. Let X be a topological space, and let us denote the unit interval by I. Let I is equal to 0, 1. So this is our unit interval. From onwards we will define this unit interval with this big I. Now a path homotopy between the paths. Now these are the paths between the paths f and g. Now since these are the paths, so they are the maps from the interval I to x. So a path homotopy between these paths. Now it is given that where f and g they have same endpoints, where i.e. where f of 0 is same as g of 0 and f of 1 is g of 1. So we are given two paths f and g with same endpoints, then a path homotopy between these two paths f and g is a map f from closed unit interval I cross I to x, such that for all x and t belongs to I. So four things must satisfy. We have, first one is, when we restrict f to 0 we should get small f. Second is, when we restrict f to 1 we should get g. Now if we restrict f in the first component to 0 we shall get the initial point. So let us keep this x0 and let us keep this x1. So we should get x0, and finally the fourth, this is third, and the fourth, which is f of, sorry, this is f of 1, 0, 1t, it is x1. So in this case f and g are said to be path homotopic, and we when two paths f and g are, suppose, are path homotopic, we write F is homotopic to G. Now I'll explain this thing in a bit, but before this we'll do an example, and I'll explain this whole definition in this example. Any two paths with same endpoints are homotopic. Suppose we have a space X here, and let us suppose we have two paths F and G. This is suppose F, and this is path G. Let us keep this point, fix this point x0, and this is x1. Now we have two paths F and G with same endpoints. Now we have to prove F and G, they are path homotopic, so we have to exhibit a path homotopy between these two paths. Solution, and let us consider the homotopy. Consider the map f of xt to be equal to 1 minus t of f of x plus t times g of x. Now this is a linear homotopy between fx and gx. Now to prove f and g are path homotopic, we have to prove these four conditions. Now let us suppose, now since now this consider a map, this map f is from interval I cross I to the space x, and it is defined by this thing. So now let us see what will happen if we first restrict t to 0 and 1, and then x to 0 and 1. Now f of x0, that is f of x, f of x1, that is called g of x, f of 0 t, that is f of 0 t is same as one minus t times f of 0 plus t times g of 0, but f of 0 and g of 0 are equal to x0, so this is 1 minus t of x0 plus t times x0, this is equal to x0, and f of 1 comma t, that is 1 minus t of f of 1 plus t times g of 1. Now both f of 1 and g of 1, they are equal to x1, so this is 1 minus t of x1 plus t of x1, so this is x1. So one can notice here all these four conditions are satisfied. Now let us check what is happening geometrically. So we have this function f from I cross I to the space x. So now this I cross I is like this. So let's define like this. And finally let us pick this color, black color here. So what is actually happening? So this is x direction and this is y direction. So this is our interval. This is 0, this is 1, this is 1. So this is I cross I. Here this is 0 1 cross 0 1. So this is I cross I here. Now this is our space x. Now we are saying that f of x comma 0, this is little f. That means now f of x 0, now this is the t direction here. Sorry, this is t direction here. So when t is 0 and x is varying, so we have this pink line segment here. So f of x 0, so these the input of capital F here is this pink line. So this pink line is mapped to the curve little f. So this is x0, this is x1. So this is over little f. Now this, it is also given that f of x1 is g. Now set of all points is x1. So x1 set of all points with second component 1, that is this green line. Now this green line, when we give inputs to capital F from this, from the pointers lying on this green line, we get this little g. So this little green line is mapped to g. Now if suppose this is here, this is suppose t1 and suppose this is t2. So this t1 line here, I mean when I give inputs from this line, that is if I look at this function f of xt1, so I am giving inputs from or first let us first consider this thing. We are saying that f of 0t, that is x0. Now f of 0t is this blue line. Now this whole blue line, this is mapped to this x naught, because it is given here f of 0t is this x naught and f of 1t is this x1. So f of 0t, so this blue line is mapped to this point here, and f of 1t, it is mapped to x1 by the above homotopy. So this cyan vertical line, this is the set of points whose first component is 1. So this cyan line is mapped to x1. So this whole line is mapped to x1. Now what happens in between is that if I take this line segment over here, this will get mapped to some curve between these two curves like this. And now if this black curve, if these points are concerned, this is gonna map it to some curve here. So during this homotopy, if I take a point here, suppose this is f of s. So if I take this vertical line segment here, this vertical line segment here is gonna get mapped to this vertical line here. So during this homotopy, if this is point s, so this is point f of s, this is point g of s. G of s, sorry, this is s prime, so this point will be g of s prime. So during this homotopy, each point fs travels along the line segment to gs prime. So this is gs here, this is the line gs here, sorry, this is point s, so this is point s. So during this homotopy, each point fs travels along the line segment to gs at a constant speed. This is because that line through fs and this gs is linearly parameterized as f of s plus g of s minus f of s times t. So this is the fixed point, and this is the line segment from these two points, which is same as 1 minus t of f of s plus t of g of s, with the line segment from fs to gs covered by t values in interval from 0 to 1. So this line segment is covered by these t values. So these are the t values in the interval 0 and 1. If f of s happens to be equal to g of s, then this segment degenerates to a point, that is, suppose these 2 points are equal, then this segment degenerates to a point, that means f of st will be equal to f of s for all values of t. This occurs in particular for s is equal to 0 and s is equal to 1. One can see that this whole line segment is gonna get mapped to this point, and this whole line segment here, this vertical line segment, is mapped to this one. Now continuity of homotopy, this f, capital F, as a map from the interval I cross I to the space X follows from the continuity of f and g, because we define this homotopy f here to be the this convex combination of fx and gx. Now being fx and gx being continuous, so this capital F is continuous. I think this is it for this lecture.